Let's say that we are given a ball that is traveling towards a wall. The speed of the ball is v, the mass is small case m, and there is a pressure difference between the ball and the outside, which we call delta p, and the radius of the ball is capital R. Now this ball will hit the wall horizontally, so this distance is very small. I just zoomed in the picture so that we can better visualize what is going on. That means you can neglect the effects of gravity or any other force. There is only the force by the wall on our ball. So this will travel towards the wall, as I said, and it will hit the wall. Perhaps it will have a shape like this. Some amount of it will be compressed. Now my question is, what is the compression distance? What is the maximum x, the maximum compression? I want to give you a couple of minutes to try this on your own, so pause the video, and when you're ready, let's do it together. Alright, I assume that you gave it a go and now you're ready to see the solution together. How do we start though? What is the best approach here? The best approach is to first draw the ball again. Let me erase this part. Alright. Now this much is compressed. Hold on a second. This much will be compressed and this distance is x. So this much is actually bended in this direction, but I don't draw it like that because I believe this is easier to visualize. This is the way I like it. If you don't like this way, if you find it complicated, you can do it however you like. So we know the radius, it is capital R. That means this distance from the center of the ball to the wall when the maximum compression is achieved, that distance is R minus X. Right? And if I call this small case r, which will be the radius of the area that the ball hits the surface, it will create a circular image on the wall, let's say, and the radius of that image is r, small case r. This distance is of course still r, the radius doesn't change. We have a right triangle. What do? We use the Pythagorean theorem. So we have r squared is equal to little r squared plus r minus x squared. Here we will use a very, very powerful statement. We will say x is less than, very less than, much, much smaller than the radius. This is huge. This statement is very important. And I hope this makes sense. When you throw a ball towards a wall, if there is sufficient delta P, sufficient pressure difference, the compression won't be drastic. It will compress a little. Perhaps you won't be able to detect it with your eyes. So we are interested in a small compression distance, which of course means if we divide both sides by r, x over r is much, much smaller than 1. We will use this fact in about a minute. So this is equal to r squared plus, I want to factor r inside the parentheses so that we get r 1 minus x over r. This is squared. Then let me distribute the square to get r squared plus r squared times 1 minus x over r, the quantity is squared. How do we proceed from this? Well, we note that this part is much, much smaller than 1. That's what we just argued here. And in that case, we can use a very powerful approximation method. That is 1 plus epsilon to the power of alpha is approximately equal to 1 plus alpha epsilon, where epsilon is much smaller than 1, and it is a positive number. Also, I proved this in a previous video. You can access that video from the cards right now and also from the descriptions part. Using this approximation, we will say this is approximately equal to r squared plus capital R squared. So, what do we have from the formula? 1, we have minus, in the original formula we have plus, that doesn't matter. You have minus, you put the 2 in front, so 2x over r. Which is, if we now distribute the r squared, equals little r squared plus r squared minus 2xr. So this and this cancels, which means that r squared is approximately equal to 2x, let me write it here, 2rx. Cool. I mean, up to this point, it might be clear to what we're doing, but you might be wondering why we're doing this. How does this help us to figure out what x is? We just introduced a new variable, small case r, so we now have 2 variables. Where are we going with this? Let me show you what I intend to do. If I want to write the motion formula for this, so if I want to write F net is equal to ma during the collision using Newton's second law, what can I say? What will be the net force on our ball during the collision? Well, as I said, you can neglect the gravity. The collision takes a little amount of time. So the only force will be by the wall. And the amount that the wall applies on the ball is equal to the amount of force that the ball applies on the wall by Newton's third law, action and reaction. What force does the ball apply? Well, the ball will apply a force, so let's call it F. The magnitude of that force will be the pressure difference times the surface area. The area of contact at any given instant. And what is the area? What kind of a shape was it? We argued at the beginning of the video, I guess, that it is a circle with a radius r. What is the area of a circle with a radius r? It is pi r squared. So the force is delta p pi r squared. What did we do? We multiplied the pressure by the surface area to get the force. Because, and you might be wondering, what happened to all these surfaces? There is pressure on those as well, but due to symmetry, these cancel. Only the contact area is our interest. It is in our interest, only the contact area. So for force, I can substitute this expression. And I put a negative because the velocity and the force are in opposite directions. This is the positive direction, this is the negative direction. The force on the ball is to the left, so it is negative. This decreases the speed, that's what I'm trying to say. Delta p pi r squared. What is r squared? Hey, that's why we did it. It is 2 times capital R times x equals mass times, what is acceleration? It is the time derivative of velocity, which is the time derivative of position. So it is the second time derivative of position, which we can show by putting 2 dots on top of x. This is the way Newton did it, so let's just do the way he did it. This is the convention for these types of problems, because we're about to encounter a very useful formula. If I add this guy to both sides, what do I get? And let's do it here. Okay, we get mx dot dot plus 2 pi r delta p x equals 0. Now if I want to divide by m on both sides, So I do that. And let me adjust the x as well. Okay. And this is the simple harmonic motion equation. I have a video about this. You can access it from the cards right now and also from the descriptions part. This is simple harmonic motion, SHM. And in simple harmonic motion, this coefficient of x is what we call omega squared. Now, how does omega squared help us? Using it, obviously, we can find omega. So let's find it. Let's do it here. Omega equals the square root of the quantity. So 2 pi r delta p over m under the square root is omega. Also, in simple harmonic motion, the maximum velocity, which is v, right? The velocity just before the collision in our problem, v equals omega times the maximum compression, maximum displacement from the equilibrium, which is x. And we found x. That's it. X equals v divided by omega. So substituting the value that we found for omega, we get that the maximum compression is equal to the square root of m divided by 2 pi r delta p. And outside of the square root, we have v. Okay? And you might be confused that we got a simple harmonic motion because the ball, when it hits the wall, it will rebound, but it won't hit it again. The ball won't oscillate. It will only undergo a half of the period of the simple harmonic motion. Alright, I want to highlight that. This doesn't necessarily mean that the ball would be like a mass on a spring and oscillate back and forth. No, it won't do that. It will just cover the half of the period in this motion and then it will go on its way. But during that half of the period, we are in simple harmonic motion and the rules, the equations, the ideas all apply. I hope this video was helpful. This is a very hard problem in my opinion. So if you have any questions, please do not hesitate to ask them. I would like to help as much as I can. So anyways, this is it for this video. If you have any questions, please add them in the comment section. I hope to see you in another video. Until then, take care.